Alexis?
Sir, the last thing we did was the general solution of trigonometric equations.
Alright, so general solution. So that means the next thing is half angles and double angles. Alright, so half angles and double angles. So that's where we'll start today. So here's something we need to know before we get into half angles and double angles. If we look at sine 2x, this is not the same thing as 2 sine x. So both of these are saying two different things. Then if we look at cos 2x, this again is not the same thing as 2 cos x, and the same would go for tan 2x, which is not the same as 2 tan x. So this is very important to note that these are not the same. Now we can look at it practically and say that if we have sine 30, this is going to be equal to a half. And if we say 2 sine 30, this is going to be equal to 1. Now I know you might be saying that if this is 30, this might be x, this is also x, this is not 2x. But let's actually look at it that way. So if we have sine 2 times 30, this is going to be the same as sine 60. And sine 60 is equal to root 3 over 2. So if we're looking at it like this, to say that the 30 would represent the x here, and this is sine 2x, is going to be equal to root 3 over 2. However, if we are looking at 2 times sine x, that's going to give us 1. So two different solutions from this. So that goes to prove that sine 2x is not the same as 2 sine x. So of course, you know, we will have various formulas for our different angles. So we have the double angle formulas and we have the half angle formulas. So double angle formulas for sine, so this is going to be where sine 2a, and based on the compound angle formula that we did the other day, how can we break apart 2a here to get it to look as the compound angle form? What did we do? You remember what we did? What did we say sine 2a could be the same thing as?
Sine A plus A.
Yes, this is the same thing as sine A plus A. And in applying the compound angle formula, this will be the same thing as sine A cos A plus cos A sine A. So if we look closely, we realize that what we have on the left, well, on the left hand side of the plus sign here is just sine A cos A. On the right hand side, it's still sine A cos A. So this is just 2 sine A cos A. And this would be the double angle for sine. And similarly, we can derive the double angle for all the other trig functions. So for cos, we can say that cos 2a will be equal to cos a plus a. And then this will be what? We're looking at the compound angle. Go ahead.
So it would be sine A minus cos A.
Sure, it's that order?
Or cos A minus sine A.
So cos A minus sine A sine A. So this on the left hand side of the minus sign is just cos squared A, and this on the right hand side is minus sine squared A. So this would be your double angle for the cosine function. And then, you know, from here we can use the Pythagoras identity to substitute for whatever we need, if that need arises. Now let's look at the one for tan. So we have tan two a. So this is just tan a plus a. And this one will be tan a plus tan a over 1 minus tan a tan a. So what we'll get in the numerator is just 2 tan a over 1 minus tan squared a, and that will be it for the tan function. So those would be your 3 double angle formulas, and of course you could have other variations of these formulas. For example, the cosine formula, we could have other variation of this. We could change out the sine squared a to 1 minus cos squared a, right? You're seeing that, right? Alright, let me just write it on another page, and we'll just look at the other variations of this. So if we have cos, let's say 2x, because it won't necessarily be, we can use any letter to represent the angle, it doesn't have to be a. So cos 2x would be the same thing as cos squared x minus sine squared x. And then we're saying that if sine squared x plus cos squared x is equal to 1. We can modify this in any way where we can substitute as the cos squared or the sine squared. So let's use sine squared as our subject. So sine squared x will be equal to 1 minus cos squared x, and then we substitute this here. So one variation of this compound angle, well, this double angle formula will be cos squared x minus, I would have substitute this 1 minus cos squared x. So this will be 2 cos squared x minus 1. So this is one variation. Another variation is if we make cos squared x the subject. So if we make cos squared x the subject, we're going to get 1 minus sine squared x, and then we simply substitute it here. So the second variation is going to be 1 minus sine squared x minus sine squared x. So it's just 1 minus 2 sine squared x. Are we clear?
Yes, sir.
Alright, so these types of questions can appear in any way, shape, or form. So it doesn't necessarily have to be straightforward. Like, what I mean is that they won't necessarily give you a question and say solve for cos 2 theta, cos 2x is equal to 5. They will sometimes give you these as hidden quadratics. So we would need to know how these questions can appear in any different setting. So for example, we have this one, 2 cos 2 theta is equal to 1 plus cos theta. Where we're going from 0 to 360. So when we get the range of values like this, we know we are working in degrees. Whatever answer we give should be in degrees. However, if they gave us from 0 to 2 pi, whatever answer we're giving should be in radians. So this tells us what our final answer will be in, or what we're working in. Alright, so let's look at how we can approach this question. So first things first, we notice that there's a double angle here, the cos 2 theta. This is a double angle, and what we're working with on this left hand side is cosine. So that means the variation of the formula that we will be using is this one, where we're working with cosine only. Because remember, this is the original formula up here now. For the cos, the double angle for cos, this is the original thing. However, seeing that the question has a cos over here, we would strictly want to be working with cos. So that means we're going to be using the variation that only has cos in it. So it's 2 cos squared x minus 1. So we'll be substituting that there. So we put back our 2 on the outside here, open bracket, and then we replace this cos 2 theta with 2 cos squared theta minus 1. And this is equal to 1 plus cos theta. And then from here on out, we expand, we bring to one side because this is going to be a hidden quadratic, and then we solve. So now this is going to give us 4 cos squared theta minus 2 is equal to 1 plus cos theta. We bring all of this over on that side. So we have 4 cos squared theta minus cos theta minus 3 is equal to 0. So this is what we have so far. So we can use our substitution to say let y be equal to cos theta. So now we have 4y squared minus y minus 3 is equal to 0. And then from here we apply AC method. So this is negative 12. So the numbers we are looking at here are negative 4 and positive 3. So we have 4y squared minus 4y plus 3y minus 3 is equal to 0. We factor out 4y, y minus 1. We factor out 3, y minus 1. So 4y plus 3 and y minus 1 is equal to 0. So our two solutions where y is equal to negative 3 over 4 and y is equal to 1. So once we have our two solutions, we can now go ahead and find where our answers will fall. Because remember we said that y is equal to cos theta, you know. So since y is equal to cos theta, so y is equal to cos theta, cos theta is going to be 3 over 4. And remember we said that we're ignoring negative sign here first, and whenever we're going to do our general solution, we know we're going to look at the region where cos is negative. So theta would be equal to cos inverse 3 over 4, and that would give us 41.41 degrees. So if we're looking at where cos is negative, so this is our Cartesian. So cos would be negative in quadrant 2 and 3, and in quadrant 2 we said that whatever answer we get, we subtract it from 180. So 180 minus theta, and in quadrant 3 whatever answer we get, we add it to 180. So this is 180 plus theta in quadrant 3. Quadrant 2, it's 180 minus theta. So that's what we'll be doing with this answer that we got to find where our solution will be. Alright, so if we subtract let's see, if we subtract from 180, we're going to get 138.6. I'm going to need to get to the next page to do that part. So this is theta. So around here we will say 180 minus 41.41, and that's going to give us 138.6. This is rounded off, and then we have 180 plus 41.41. This is 221.4. So these are two solutions so far. And then remember we have this other solution here where y is equal to 1. So we're going to say cos theta is equal to 1. So theta is equal to cos inverse of 1. So that's what? 0. So theta is equal to 0. And this one we're looking at where cos is positive. So that's in quadrant 1 and quadrant 4. So that means one of the solutions is 0. Let's check something real quick. Alright, so 0. And of course, if we're looking at quadrant 4, we would say 360 subtract 0, that's going to be 360 still. So these would be our solutions. So therefore, theta is equal to 0, 138.6, 221.4, and 360 degrees. Is that clear?
Yes, sir.
So the only part of this question that should be a bit new to you is this part where we substituted the double angle, but everything else is what we have been through before, so it shouldn't be too bad. Alright, so let me see if I can get a question, and then we'll do one more, and then we'll look at half angles. So this is double angle. And then of course, you know, these double angles can be used in your proofs as well. So I'm going to do one of those questions. I think that's mostly where you'll see it, where you'll have to prove something. Alright, so I don't want to get one that's too difficult. Alright, let's look at this one. Prove the following, or prove that this is true. If we have 1 minus cos 2x being divided by sine 2x, and we are told that this is identical to tan x, we need to prove this. So what will happen is that we'll need to substitute our double angles here and here. So let's see which one we can use. So for the cos, so seeing that there is a sine down here, sine 2x, what we're going to do is, for this one, we're going to use the sine variation. So the sine variation is this one. So that's the one that we're going to be using, 1 minus 2 sine squared x. So we'll say 1 minus, and then we replace this with 1 minus 2 sine squared x divided by, and then we'll look at double angle for sine 2x. So the double angle for this one is 2 sine x cos x, and this must be equal to tan x. Alright, so let's expand. So this is 1 minus 1 plus 2 sine squared x divided by 2 sine x cos x. And then what this will work out to be is 2 sine x sine x, because that's what sine squared x is, right? Sine x divided by 2 sine x cos x. So what we have now is sine x cancelling sine x, 2 cancelling 2, so we're left with sine x over cos x, and this is just tan x. Put your QED, you finish. Pretty straightforward, right? So all that's required of you is to remember these double angles, and even if you don't remember them, you can actually derive them. So you don't necessarily have to remember them, you can just evaluate them. So you could say sine 2x is the same as sine x plus x. So you don't have to remember what this works out to give, you can just work it out for yourself. Clear?
Yes, sir.
Alright, so let's look at one other way which these types of questions could be structured. So these types of questions can also be structured in the form of acute and obtuse angles. Suppose x is an acute angle such that sine x is equal to 1 over 5, and we are required to evaluate sine 2x. So if x is an acute angle and we need to evaluate sine 2x, we must first write what sine 2x is. So we should know that sine 2x is the same thing as 2 sine x cos x. So 2 sine x cos x, that's what sine 2x is. But based on the information they gave us sine x. So we would need to evaluate cos x from this. So let's see what our triangle will look like. So this is an acute angle. So an acute angle, and this is where sine is positive. So it could either be on here or here. However, sine is equal to opposite over hypotenuse. So that means we're dealing with something on this side of our Cartesian plane. So it would look something like this. 90 degree here. We have 1 and we have 5. So the side down here, let's see. So if this is, so using Pythagoras theorem, we have 5 squared minus 1 squared will be equal to down here. Let's not call it x. Let's just call it the adjacent. So that's the adjacent down here. And that's going to be equal to the square root of 24. So square root of 24 is the same thing as, so that's what, 4 times 6. So it's 2 root 6. So this is what this side measures, 2 root 6. Alright, so we know what the adjacent is. So we will say cos x is equal to adjacent over hypotenuse. So that's 2 root 6 over 5. So this is what cos x is equal to. So we have all of that information. We can now go ahead and substitute. So 2 times sine x times cos x, and then we evaluate this. So this is 2 over 5 times 2 root 6 over 5. So this is 4 root 6 over 25. And this would be our solution. And if they wanted us to find cos 2x from this, we could also do that. So let's say they wanted us to find cos 2x. Cos 2x. So cos 2x, we can write this as cos squared x minus sine squared x, and with a substitute, because we know cos x is 2 root 6 over 5. So we square that and we subtract 1 over 5 all squared. So this will be 4 times 6, 24 over 5 over 25 minus 1 over 25. So this is just 23 over 25. And of course we could do the same with tan 2x. All we'd have to do is to find what tan x is from this, and tan is opposite over adjacent, so it's just 1 over 2 root 6. So we can approach this in many ways. We just have to pull back on what we did previously. So whatever topics we did in trig, they will always be merging together. So just remember that. So the double angle will come into play where we have the compound angles. Compound angles will come into play when you're dealing with acute angles, obtuse angles. Even Pythagoras theorem will come back into this. So all of these concepts are linked to each other. So that's a key point to note whenever you are doing this. Alright, let me see if there is anything different before we get into half angles. Alright, so let's look at this one. The examiner tells us that tan x is equal to 2, and x ranges from 0 to pi over 2. We're required to find sine 2x. Alright, so from this, wait, this is a continuation question. So this part wouldn't be valid without the previous parts. This is one of the acute angles as well. So it's, all you'd have to do is to find sine x from the triangle, cos x from the triangle. So this is a continuation from a previous question. Alright, simplify. Two sine 75 cos 75. So for this, cos 75 is, so 75 what's that? 512. So 5 pi over 12, and this can be broken apart into so this can be broken apart into, let's see, 3 and 4. Two pi over 12. So this is 2 pi over 6 plus pi over 4 cos pi over 6 plus pi over 4. And then a question like this, you could simply just put it in your calculator, evaluate it. So on this side we will be left with 2 root 6 plus root 2 over 4 times root 6 minus root 2 over 4, and this will result in a half. So you could just put all of this in your calculator. Because most of the times these are just worth 2 marks, 3 marks the most. And these are just various trig concepts being intertwined. These aren't necessarily double angle or half angle. So as stated, the double angle, all we would need to do is to know the general form for it, and then we substitute. But besides that, nothing much really. And the same would go for half angles. We're just looking at the formulas that would govern these. So let's look at the half angle formulas. So half angle formulas. And firstly we look at the sine. So this is given in the form sine x over 2. So this is plus or minus the square root 1 minus cos x over 2. The half angle for cosine so we have cos x over 2 and this is equal to plus or minus square root 1 plus cos x divided by 2, and the half angle for tan this is sin x over 1 plus cos x and this is equal to 1 minus cos x over sin x. So we have two variations of this one. Alright, so we will be looking at how the half angle is applied. We'll be looking at how this is applied. And what the examiner normally does is they usually like to give half angles for some reason. So they will say use the half angle formula to show that something is equal to something. So we'll look at how this is used. So there are three different formulas and we'll see how we can apply them. Alright, so an example here. Use the half angle formula to show that, or to solve sine 105 or 105 degrees. So they will say use the half angle formula to solve something, and we need to do it in this case. So what will happen is that we need to basically get this to be looking like the half angle formula. And the half angle formula for sine is, well, how it's written on the left hand side is that it must be in the form sine x over 2, right? This is showing that we're half in the angle. However, what we have here is sine 105 degrees. This isn't represented in the half angle form. So what we must do is find what angle we can take the half of to get 105 degrees. Is that clear?
Yes, sir.
So we need to think to ourselves, what can we take the half of and get 105? The answer for that would be 210. So we can say sine 210 divided by 2 is going to be the same thing as sine 105. So that's the idea behind this. So now, once we have this written, we will go ahead and apply the formula. So we will say square root plus minus the square root of, so the sine half angle is 1 minus cos x divided by 2, So we say 1 minus cos 210 divided by 2. So this would be the representation of this problem. And then we will say this is equal to the square root of 1 minus, so cos 210 is going to be negative root 3 over 2, and we divide by 2. Let's bring this down a bit. So this will now be square root so the square root of, so this is plus, so it's 2 over 2 plus root 3 over 2 all divided by 2. So we're just getting an equivalent fraction for the 1. And then lastly, this is going to be square root of 2 plus root 3 all over 4. And you'll notice that I dropped the plus or minus sign here. Reason for that is because this is sine 105 degrees. And if we look at our Cartesian, sine 105 would be somewhere over here, and this is where sine is positive, so we have to take the positive solution. Clear? Alright, so I can't see the chat, but I'll take it that you're saying yes, everything is clear. Alright, so what I'm going to do now is I'm going to give you one to try, and I'm going to give you 4 minutes. So the one that you'll be doing is you're going to use half angle to solve sine 75 degrees. So I want you to solve this and take a picture of your solution, send it in the group. So you have 4 minutes. So let's write it off. Sine 75. I'm going to go back to this page where you can see how I worked it. So let me know when you have this. When you, well, it's just sine 75. So this is the previous one. So you have 4 minutes to do this. When you're finished, just send the solution in the group. finish. Alright, so I'm not seeing any responses in the chat. Alright, so let's get through this one. So sine 75, and if we're looking at what this might be equal to, we can say that this is the same thing as sine 150 over 2, where 150 is going to represent our x, and this is going to be plus or minus square root 1 minus cos 150 we put that over 2. So this is plus or minus square root 1 minus negative root. Oh, same thing, 3 over 2 divided by 2. So this basically gives the same as the one previously. So this is going to be 2 plus so this is 2 plus, well, 1 plus, let me see, wait, let me double check this.
Sir, the 3 over 2 is fixed. So?
What do you mean if it is fixed?
Because the question before the example had 3 over 2 as well.
Coincidence.
The one coincidence?
I'm double checking it. Alright, so this one is 2 plus root 3 over 4. But that's what we got for the first one.
So how did you get 4 as a denominator?
We're dividing by 2. So root 3 over 2 divided by 2. So we keep change flip, so that will become a half times a half. So let me double check this one as well. So this one, it's the same thing, so that means this is, the 4 is right here. And let me just check cos 210. Yeah, it's the same. Let me check cos 150. Same. So it's just a coincidence that both of these ended up being the same thing. Alright, so let me just go through 2 more examples. One where we're looking at a cosine half angle. One where we're looking at a tan half angle. So let's quickly get through that. So for this one we have cos 135. And if we're looking at the angle which we could take to get the half of this, is going to be 270. So this is going to be cos 270 divided by 2. And this is plus or minus, let's see, cos 135 CAS. So cos is going to be negative over here. 135 is going to fall here, so we're going to be focusing on the negative solution. So this is negative square root 1 plus cos 270 divided by 2. So cos 270 is 0, so this is negative square root 1 plus 0 . So this is just of a half, which can be broken down as square root of 1 over square root of 2, and that's negative root 2 over 2. So this would be your solution for the half angle for cos 135 degrees. Is that clear?
Sir, can you go again, please?
So what we did here, we got the half angle. Well, we got the question. This would be the question. Use the half angle formula for cosine to solve this. And they probably would say give it in its exact form. Alright, so this is cos 135 degrees. So first things first, we look at our Cartesian plane to see where 135 would be, and it would be over in this quadrant. And over in this quadrant, only sine is positive. So cos would be negative over here. So that means we're going to be taking the negative solution. That's why you see we have the negative sign out here. And then we said that, seeing that we're using the half angle, what angle can we divide by 2 to get 135 degrees? And that angle would be 270, because if we divide 270 by 2, we'll get back 135, right? Is that clear?
Yes, sir.
Okay.
Yes, sir.
So now, remember, when we write it as the half angle form, it's written as cos x over 2. This x here is the angle we're going to divide back to get the original angle, which is the 270. And then in the formula, all we're replacing is the x. So in the formula that we were looking at for cosine, this is just cos x. So we're only replacing the x. So that's what we did here. We replace the x with the 270. And then we evaluate what cos 270 is. That's 0. So we put in with 0. So this is just a half. So the square root of a half. And then based on the laws of indices, if we're taking the square root of a fraction, the radical can be written on the numerator and on the denominator as separate terms. So this is square root of 1, square root of 2. We know that the square root of 1 is just 1. And this is 1 over root 2. And then we use surd to go from here to here. We'd multiply by root 2 over root 2. And then we get this down here. Is that clear?
Yes, sir.
All right. So this would be the example for cosine. We want to look at one for tan. Alright, so let's see. So remember, you know, what we're doing is just substituting. The idea would just be remembering the formulas, and then we can just substitute the angles. So for tan, we have tan 15 degrees. Same scenario. What angle? When we take the half of it, we get 15. That angle would simply be 30. So this is just tan 30 over 2. Clear? And then we simply pull up the half angle formula for tan. So this is going to be equal to square root, and we're going to be taking the positive of this because, as we know, everything is positive here. So tan 30 would fall here, tan 15 would fall here. So we have to use the positive variation. So this is the square root of sine x, which would be 30, divided by 1 plus cos x, which is 30. And then we just simplify this. Sine 30 is a half. Cos 30 is root 3 over 2. So we just simplify those. So that's a half over 1 plus root 3 over 2. So this will be root 2 over 2. So it's 2 plus root 3 over 2. Let me see. So this is a half divided by 2 plus root 2. So this is a half times 2 over 2 plus root 3. So this is 1 plus 2 root 3. And then there is something specific about the tan. Oh, this is a square root. There should be a square root sign here now. Alright, so for this, for the tangent half angle, what happens is that the final solution will be flipped. I think it will be accepted as either one because it's going to give the same solution. It should, but I'm going to double check it. Should give the same solution. Let me check something. Alright, so it's 2 minus root 3. Apologies, let me just get rid of this. I don't know why I had the square root on that one. Alright, so I think this should be fine now. We have it as 1 plus that. Alright, so this part here works out to give, so we're dropping the square root, 1 over 2 plus root 3. This is what this part works out to give. But based on what we should do for this, we're going to flip it and then change the sign. So it's going to work out as 2 minus root 3. This is how the half angle for tan works. Whenever we get close to the final answer, so we were working it with this part, sine x over 1 plus cos x, but whenever we get to the final answer, it's going to be flipped. So what we could do is flip it and then we do our substitution. So that's an alternative. Instead of flipping it at the end, we could flip it, then do our substitution here. But it's just to practice. I'm going to try and source as many questions as possible. And well, even though we have the past papers, when we're having our second session, I'll see if I can include some more of these based on what the structure is on the past paper. So that's how we would apply these half angle formulas. The idea is just to identify which angle we would take the half off to get what we need, and that would basically be it for the half angle formulas. I'm seeing if there is anything else in the textbook, any other types of examples that we can use. Everything else is just to prove, and all we're doing is just rewriting the formulas. So for example, if they asked us to find cos 4a, we could say that's cos 2a plus 2a, and then we just break it apart. So that would include multiple double angles in one. Alright, so that's basically it for half angle and double angle. So the next thing we'll be looking at is the form a cos theta plus b sine theta. So a cos theta plus b sine theta, and this is just one of those general forms that we use in trig. So an example, we'll start off with an example for this one. So express a cos theta plus b sine theta in the form r cos theta minus alpha, where r is greater than 0 and alpha falls between 0 and 90 degrees. Alright, so let's see how we can approach this one. So this one will be using Pythagoras theorem as well as a little Pythagoras theorem will come into this one in terms of the circle formula and the radius and all of that. Alright, so let's see. So let a cos theta plus b sine theta be equal to r cos theta minus alpha. So what we're going to do is use the compound angle for cos to expound on that side. So if we do that, what we're going to get is r cos theta cos alpha plus sine theta sine alpha, and we have our r on the outside, and this is going to be equal to a cos theta plus b sine theta. Is that clear? What we did over here is just to use our compound angle and get it like that. So is that clear?
Yes, sir.
Alright, so we have it written in that form. So let's distribute our r. So we're going to be distributing the r to the cos here, the r to the sine over here. So let me just... Alright, so a cos theta plus b sine theta is going to be equal to r cos theta cos alpha plus r sine theta sine alpha. So far we haven't done anything too tricky, just distributing and expanding rather. Alright, so let's see what else we can do from this. So what we could do is equate coefficients, or equate the parts that are similar. So we have a cos theta here, we have r cos theta cos alpha. So we could say that these two pieces are the same as each other. So a cos theta is equal to r cos theta cos alpha. Then cos theta cancels cos theta, so a would be equal to r cos alpha. And similarly, we could say that b sin theta is equal to r sin theta sin alpha. So b is equal to r sin alpha. So we have a is equal to r cos theta, b is equal to r sin theta. So we have that so far. So now we can combine both of these to say, what if we were supposed to divide b by a? If we did that, I think you can see where this is going. If we say b over a, that's going to be equal to r sin alpha over r sin, well, r cos alpha. And the r's will cancel. And what will this give us? B over a is equal to what?
So tan alpha.
Tan alpha.
So question, how did you remove the cos theta and the sin theta from both of the equations, sir?
We basically divide by cos theta here, and then we divide by sin theta here, sin theta. So those cancel out.
Oh, okay, sir.
So now we have b over a is equal to tan alpha. If we were ever required to find alpha, we can just take the inverse. So alpha would be equal to tan inverse b over a. This formula, is trying to put my finger around where this formula is from. I can't remember the exact. Alpha is equal to tan inverse b over a. Let me check. This formula is very familiar. Give me a second. I think it's just the angle that would be formed between the tangent, if we're using the tangent function. Alright, so that's how we would go ahead and solve for alpha. Of course, we'll be getting some practical examples. So if we were required to solve for r, so this is how we solve for alpha. And then you'll see when we get some questions how we can do it. But for now, if we were required to solve for r, so solving for Let's use a capital R. So we said that A is equal to R. I don't know what, let me use the common R. Let me use the common R. So A is equal to R cos alpha, and B is equal to R sine alpha. What we could do is to square both sides, and of course you know this will come into play with the Pythagorean identity. So if we square both sides, so squaring everything, so if we square everything here, A squared is going to be equal to R squared cos squared alpha. B squared is going to be equal to R squared sine squared alpha. And then we can just combine both equations, where we will have A squared plus B squared is equal to R squared sine squared alpha plus R squared cos squared alpha. So A squared plus B squared, we can factor out the R squared, and we're left with sine squared alpha plus cos squared alpha. This is going to be equal to 1. So A squared plus B squared is equal to R squared. And then, you know, we can just take the square root of both sides. So square root in both sides, R is going to be equal to the square root of A squared plus B squared. And this looks very similar to, well, if A and B were X and Y, this would have been very similar to our circle equation, where the center is at the origin. Alright, so let's look at the different variations to how we could get these types of questions. So remember, the idea is that this is closely linked to the compound angle for cos and sine. And we know that there are two variations of each. So this is something to note. There are two variations of our compound angle for sine. So we could say R sine open bracket theta minus alpha. This would be one variation. Another variation is R sine open bracket theta plus alpha. So these will be the two variations for sine. One where we have a negative, one where we have a positive. Similarly, R cos theta minus alpha, this is one variation, and then R cos theta plus alpha. So all of these variations are going to give something a little bit different. So it all depends on which one we're using, and based on the question, that will determine which one we use. Alright, so we've established that, let me separate this here. So we established that A cos theta plus B sine theta is equal to R cos theta minus alpha. So that's, as I've stated, one variation. And we established what r is. So meaning that a cos theta plus b sine theta is equal to, so remember we said that r is the same thing as square root of a squared plus b squared. So this would be, let me use a different color. So r is the same thing as square root of a squared plus b squared. I think I should put that in the next line. Put it down here. So this is equal to a squared plus b squared, the square root. Now put back our cos, open bracket, theta, and then we said alpha is the same thing as, so this is minus, tan inverse b over a. You'll see how all of this come into play once we get to the example. But this is what we're working with so far. So we'll look at an example to see how this is done. So the question would be something like this. Express 2 cos theta plus sine theta in the form r cos theta minus alpha. Alright, so let's analyze this for a second. So they're saying to us, we need to express 2 cos theta plus sine theta in the form r cos theta minus alpha. But what we need to do first is we need to assess and analyze what would represent our a, what represents the b, what represents the r. So first things first, if we're looking at the general form where we have a cos theta, we know that the a is the coefficient of cos. So that means a is equal to 2, right?
Yes, sir.
And b would be equal to 1 because there is an invisible 1 in front of the sine theta. So we know what a is, we know what b is. So we can go ahead and find r, because r is equal to square root of a squared plus b squared. So we know that r is going to be equal to the square root of a squared plus b squared. So let's evaluate. So that's square root 2 squared plus 1 squared. So that's just the square root of 5. So this is what r is equal to, root 5. So we know a, we know b, we know r. So next up, we need to find, so let's see what we have. We need to find alpha. And we are told that alpha is equal to tan inverse b over a. So we need to find that as well. So alpha is equal to tan inverse b over a. So this is just tan inverse 1 over 2. When we evaluate this, we get 26.57 degrees. This is what alpha is equal to. So we have a, we have b, we have r, and we have alpha. What do you think we should do now?
So I must substitute the values into the form.
Exactly. We know everything we need. All we do is just substitute in the form. So replace. So the R would be replacing that. Alpha would be replacing that. And we're done. So therefore, 2 cos theta plus sine theta is equal to R, which is root 5 cos open bracket theta minus alpha 26.57, and this would be your solution. Any questions on that?
Sir, could you go back to when you found R? Like the equation for R, not the answer. So how would you know when to solve for R?
You would always be required to solve for R. To put it in the form, you would always be required to solve for what R is.
So that formula for R is a fixed formula, or?
Yeah, this is the general formula for R.
Okay, sir.
Alright. So I have a few more examples here. And then I think this is a past paper question. And then we'll look at the last two topics for trig, product to sum formula and sum to product formulas. And let me see what time it is. Alright, we're going strong. We haven't touched 2 hours as yet, so we shouldn't be tired as yet. Alright, so let's do a few more examples to see where this is going. So once again, we need to solve. So we have 3 cos theta plus 4 sine theta is equal to a half, where R is greater than 0. And so R is greater than 0. Theta lies between 0 and 360. So when we see this, it tells us that whatever answer we're given should be in degrees. Alright, so first things first, let's find, well, we can highlight that A is equal to 3, B is equal to 4, and then R is going to be equal to the square root of 3 squared plus 4 squared, that's 25, so R is equal to 5. So we have all of that so far. Then we say that theta is equal to tan inverse of B over A, so that's tan inverse 4 over 3, and that's going to give us 53.13. So this is our alpha. Alright, so we have that so far. But if you notice, what do you notice about this one? Let me see if you are quick on your feet. So look at the first one we did. it said express that in the form whatever whatever. But look at this one. What do you notice being different?
So this question is equated to something.
Exactly. So
This one is like,
for this one, we're solving. So seeing that we're required to solve for this one, we can't just substitute and then say, okay, that's our answer. We need to actually solve this to get something. But first we can write it in the form to say that 5 cos theta minus 53.13 is going to be equal to a half. Because this is the same thing as 3 cos theta plus 4 sin theta, right? On this side. That's the same thing. So now what we need to do is transpose. We want to get theta by itself. So the first thing we need to get rid of is the 5. This 5 is multiplying, so we can simply divide by 5 on both sides. That will cancel, and this is going to be 1/10. So cos theta minus 53.13 is equal to 1/10. Good? Alright, so how do we get rid of this cos now? That's the next question we need to ask ourselves. And the short answer to that is we can take the inverse of cos. So what we have now is theta minus 53.13 is equal to cos inverse of 1/10, sorry. And evaluating this is going to give us 84.3. So we can say that cos, and we're going to have two solutions. You know why? You know why we're going to have two solutions?
so are you gonna, because you're going to split the fraction inside the bracket into 2, or?
Remember, you know, whenever we're dealing with trig, well, at this level, and we get an answer. So we said that cos inverse of 1/10 is going to give us 1/10 is going to give us 84.3. This is what it works out to be. But remember, what we're dealing with is a range of values that falls between 0 and 360. And we know that there are various regions on our Cartesian plane where we can get that same answer. We can get back 1/10. If we take cos of that angle, we get back 1/10. So we need to look at the other regions where we're going to get back 1/10. So 84.3 would be one of the values here, and the other one would be where? Which quadrant are we dealing with? Where cos is positive. So this is in quadrant 1. Which other one?
Quadrant 4, sir.
Quadrant 4. And what do we do in quadrant 4?
We take 360 from the angle.
Go again?
We take the angle from 360.
Yes. So to get the other value we're working with here, so one of the solutions is going to be theta minus 53.13 is equal to 84.3. We transpose to get one of these solutions. So now the second solution is theta is going to be, well, theta minus 53.13 is going to be equal to 360 minus 84.3. We have to subtract 84.3 from 360 to get the other angle over here. And when we work that out, we get 275.7. So this is where our other solution would come into play. Let's bring this up a bit. So remember, we aren't finished as yet, we still need to solve for theta. So to get theta for this first solution, we transpose. When we transpose, we get 137.4. And then when we transpose, theta now becomes 328.8 degrees. So these would be our two solutions that would satisfy this equation. And we can actually test them to see if that's the case. Where is my calculator? So let's test these to see. So we have 3 cos 137.4 plus 4 sine 137.4. And as you can see, roughly 0.5, right? Which is the half that they indicated to us here. And then if we test the other angle, 328.8 and 328.8, see, roughly 0.5 again. Clear? And this is why I say math is one of the best subjects, because we can always verify our answers. We can simply substitute and verify our answers, so we know that we're definitely on the right path. Alright, so as promised, we'll do one more example, and then we'll look at how else these types of questions can be manifested. Alright, so this one says express. I think this is a multiple part question. Yes, so I guess this one continues to I think this one continues to other genres of questions. So f theta here means a function of theta, and this is equal to 3 sine theta minus 4 cos theta in the form Alright, first things first, what do you notice about this one?
We're using sine instead of cos.
So for this one, we're using sine instead of cos. but that wouldn't affect what we do. The procedure is still the same. So where are we? I think something has been left off this question. Hold on. Let me double check this question. I think something was left off. Let's see. I think this should be equal to 2, but I'm not seeing it. I think there was another part. I think it's a past paper question, and there's another part that says, hence solve 3 sine theta minus 4 cos theta equal to. I'm going to just put that there. I think that should be there. But first things first, it says express in the form r sine theta. So in this case, a would be equal to 3, b is equal to 4. Yeah, because cos inverse. Is everyone still with me, or wanna go and sleep?
Sir, we don't sleep.
I believe you.
Sir, hanging on by a thread and trying to understand as much as I can.
Not to worry. When you get the video, just watch it over 10 times and you'll be fine.
Okay, sir, that's very reassuring.
Let me double check if it's actually recording. Okay, it's still recording. I'm just double checking something with this question because something was missing. I think this is a past paper question as well, you know. So I want to check to ensure that I have the question correctly. Alright, it should be fine. Yeah. Alright, so let's work this one. So A is 3, B is 4. So this is similar to what we worked out before. R would be 5 and alpha would be 53.5. So r is equal to 5, alpha is equal to 53.13. And then if we're expressing it in the form, we could say 3 sine theta minus 4 cos theta.
Sir?
Yes?
How can r equal 5 when the formula says that it's the root of a squared minus b squared, and a is 3 and b is 4?
It's plus.
Oh, wait. Oh, because I thought it was different numbers, sorry.
It's still plus regardless.
Okay.
So this would be equal to 5. So it's r cos, well, r sine. So 5 sine theta minus 53.13. And this would be your solution. Alright, so then they will say, so I guess this is part A, AI, and this would be II. Hence, solve 3 sine theta minus 4 cos theta is equal to 2. This would be the second part. So we already established what this is equal to, so we could say that this is just, so 5 sine theta minus 53.13 is equal to 2, and then we divide by 5 on both sides. Five going with 5, so sine theta minus 53.13 is equal to 2/5. So we take the sine inverse of that. So theta minus 53.13 is going to be equal to sine inverse of 2/5. Then from there, so we're dealing with positive sign. So sine is positive in quadrant 1 and 2. In quadrant 1, we would leave the angle. In quadrant 2, we subtract the angle from 180. So sine inverse of 2/5 gives us 23.58. So that's what we get there. So theta is equal to, or theta minus 53.13 is equal to 23.58 degrees. So that's one of our solutions. The other one would be when we subtract 23.58 from 180, and that's going to give us 156.42. So theta is equal, why do I keep writing that? 53.13 is equal to 180 minus 23.58. So theta is simply 76.71, and theta is equal to 209.53 degrees. And of course, we're going to double check these to ensure that our answers are correct. If not, something went wrong. So we have 3 sine 76.71 minus 4 cos 76.71, and as you can see, that's equal to 2. Then we'll try the other answer, and as long as one answer is correct, the second answer, as long as we follow procedure, should be correct as well. 209.53, 209.53, and 2 again. So that's the beauty about math. You just fact check, double check your answers to see if your answer is correct. So are we clear?
Yes, sir.
So this isn't the end of the question. Of course, we still have a little bit more part to this question. So this will be part A. Then part B now says, what is the minimum value? So what is the minimum value Nice. Someone's mic is open. You have a question for me? Alright, so I think we can go to Desmos and actually visualize this. So this question was a what? A sine graph. So sine x. Let me zoom in a bit. Alright, so this is our sine graph. And if we're looking at this would be 1 sine x, right? And 1 sine x would have a maximum value of 1, a minimum of -1. Let's look at 2 sine x to see what that looks like. So 2 sine x, so this is a periodic graph, it repeats to infinity. So it would continue repeating that same pattern all the way throughout to infinity. So if we're looking at, so the question gave us 5 sine something, whatever that angle is. So that what that is saying to us is that the maximum that our graph is going to reach is 5. The minimum that the graph is going to reach is -5. So what I'm saying to you now is the R value that we have in our question, when we write it in the form R sine theta minus alpha, this R value is going to indicate our maximum or minimum. A positive R value is going to indicate a maximum. So a positive R, and we have a negative R. This would indicate maximum value, and this would indicate our minimum. So from the question, we had 5 here for R. However, what they're asking us is what is the minimum, and we know that a sine graph is periodic in nature. So our sine graph would start off like this. So it would start here, go all the way up to positive 5, come back down, go all the way to negative 5, and then come back and touch. So this will be one period, which is at 2 pi. So the maximum value that we can get from this graph, seeing that our r is 5, is going to be 5. The minimum value that we can get from this is going to be negative 5. Is that clear?
Yes, sir.
So we can say that the minimum value is negative 5. The minimum is negative 5. And that's like a 1-mark question. So we establish how we can identify the minimum or maximum from one of these graphs. Additionally, if we're looking at a trig equation, other parts that are attached to the equation can shift the graph. So the r value here is referred to as the range of our graph. So I think I should make a note of that somewhere. So this would be the range of the graph. And it's basically bounding the graph to a specific. The graph can't go above 5 here and it can't go below 5. So that's the range that the graph is squeezed between. So if you ever see a question where they ask you for the range of a graph, that's what they're referring to. And remember, you know, range as it relates to functions, range would be the possible y values. You remember that? Domain is the input, the range is the output. So if they want the range of a graph, it would be between the maximum and minimum y values that we can get from that graph. And as it relates to a sine graph or a cos graph, the maximum and minimum are determined by the range, because similar to what we have for the sine, let's say we had 5 cos x. As you can see, the cos graph is indicated by purple. So the cos graph is indicated by the purple one here. The maximum that we get from that is 5, the minimum is negative 5. So it's very much similar to the sine graph. The range will be very much the same. So those are the properties of this. Oh, what else I wanted to say about this is that the graph can shift. So let's make a note of this. So this is something to note again. If we have a graph, for example, y is equal to 3 cos x minus 4. So I'm going to ask a very important question here. So ignoring this minus 4, right? What would be the range of this graph? Ignoring the minus 4. It's not a trick question. What would be the range?
Sir, negative -4 is
No,
-4 is
we are ignoring the -4. We're just looking at
oh
this part here alone. What is the range? Remember, it's in the form r cos something, you know.
sir, would it be -3 is less than x, which and x is less than +3?
Well, less than or equal to, because the 3 can be included.
Oh,
So
okay.
this would be ranging from +3 all the way down to -3. However, if we have a general trig function and there is an addition or subtraction of a constant attached, this is going to cause the graph to shift. So this determines a shift in the graph. And this is negative, so we know that negative is either down or to the left. So either down or to the left. However, in this case, we're dealing with a downward motion because the cosine function is just going to be squeezed between one specific range. So what we have here is a shift downward. So if the original range, so look at this. This is our graph. This is our graph right here. This is the cosine graph, so it's going to start at 3 all the way down to -3, come back up and end at 3 and -3. Alright, so this is our cosine graph, and we're saying that this is going to cause the graph to shift downwards 4 spaces. So that means if the graph is shifting down 4 spaces, the new point where the graph is going to start is at -1, and let me extend this. -7. So this is going to be like that. Come back up like that. Try and get it as not drawn to scale. But the idea is that if we have a value, a constant here, it's going to shift the graph either up or down. So you realize that the starting point here has been shifted down 4 spaces, and the lowest point has been shifted down 4 spaces as well. Originally, the lowest point would have been at -3, but seeing that this shift the range of the graph, we're now down to -7 as the lowest point. We're shifting down 4 spaces. So we shifted the graph down 4 spaces. Can you see that?
Yes, sir.
So now the maximum would be -1 and the minimum would be -7. So if ever we are to get a question like this, we have it in this form and they ask us to find the range of the graph. The range is just represented by the r value. So the plus or minus of the r value would indicate the range. The plus r would be the maximum, the minus r would be the minimum. So let me just give a quick thing to note. So the range of value So the max and min in interval notation. So if we were to write this in interval notation, square brackets would indicate that the value to that side is included. So what this is saying to us is the y values are ranging from, so this is saying to us that y values range from -3 to +3. These are saying the same thing. Just another notation of how we would write it. So y, given that, I think we can attach this as well. Y is an element of real numbers. So this is how we would represent this if we were asked to write it in set building notation or interval notation. So we have two different ways we could represent this. But I don't think that would be detrimental if it is not represented exactly as how you see it here. Alright, so let's look at the last two subtopics on the trig. Product to sum formula and sum to product formula. So these are, I think I have a document with, I don't have it, I brought it to school and I even brought it to class one day because what I was planning to do was to scan it and send it to you guys. It's basically a formula sheet that comprises of all the formulas that you will encounter in Unit 1. But I think I left it at school. So when I get back, I will scan it and just send it to you guys. But I'll double check if I have it here with me later on. Alright, so now we have product to sum formulas and sum to product formulas. So these are another set of formulas that you'll have to remember. So we have our product, so product to sum formula, and there are 4 of them. So one of these would be cos A cos B, and this is going to be represented as half open bracket cos A plus B plus cos A minus B. I'm thinking there must be a formula sheet on the exam paper, right? Because I don't recall seeing any. Even on the past papers, I don't recall seeing any formula sheet or...
No sir, when I was practicing for the mock exam, I didn't see any formula sheet on there either.
But there must be something. I think... I'm not sure, but I think what they do is when you go in the exam, they will give you a booklet that contains some formula. I'm trying to remember if that was the case. I need to confirm with. I need to confirm something, but I think that's what they did. Let me send a message to someone. So I'm asking Danny if they got a formula sheet last year, because I just can't remember seeing a formula sheet anywhere. And there are so many formulas, it would be cruel not to have a formula sheet. Alright, product to some formula. So that's one of them. We have another one here. Cos A sine B is equal to half sine A plus B minus sine A minus B. And then remember, all of these we're just substituting. And then lastly, we have sine A cos B Alright, so these are our 4 product to sum formulas. And we'll see how they come into play. Alright, so let's look at an example. So using the product to sum formula, evaluate sine 75 sine 15. So all we will be doing now is to just look at which one applies to this. So we're taking sine of 2 things, so it would be this one, right? So we look at what it says and we substitute. So this would be your A, this would be your B. So in substituting, we're going to have half cos 75 minus 15 minus cos 75 plus 15. So this is a half cos 60 minus cos 90. So cos 60 is a half, so it's a half, and cos 90 is 0. So this is just a quarter. Clear?
Yes, sir.
So that's all we're really doing with these formulas. They will give you something like this, and then you just use the formulas to substitute a and b and simplify, and that's it. And similarly, that's what we'll be doing for the sum to product as well. For the sum to product, we will be doing something very much similar. Then we simplify, and that's it. So let's look at how those formulas are. So these would be the sum to product formulas. So the first one on the list is sine A plus sine B. We have sine A minus sine B. That's equal to 2 sine A plus B over 2 cos A minus B over 2, and this one is equal to 2 cos A plus B over 2 sine A minus B over 2. Then we have cos A plus cos B, and this one is equal to 2 cos A plus B over 2 cos A minus B over 2. And lastly, we have cos A minus cos B. This is equal to negative 2 sine A plus B over 2 sine A minus B over 2. So these would be our 4 sum to product formulas, and we'll look at an example to see how this is applied. Then we'll do 2 more examples that follows, and that would be it for trig. Let's see how this is done. So an example. Use the sum to product formula to change sine 70 minus sine 30 in a product. So it's either we're given these things to change from a sum to product or a product, as the name suggests. So we're changing sine 70 minus sine 30 to a product. So if we need to change this to a product, we need to look at which one applies, and it would be, so this is sine and sine, it would be this one. So we're going to say A is equal to 70, B is equal to 30. So this is going to be 2 cos 70 plus 30 divided by 2 sine 70 minus 30 divided by 2. So this is just 2 cos 100 over 2, that's 50, sine 40 divided by 2, that's 20. And that would be your solution. And of course, you know, life won't always be that easy, where they give you numbers. They could also give you variables to work with. So I'm looking for one of the more difficult ones if I see any. And then, as you know, these things won't necessarily show up like this. Sometimes they could give you these to use with other concepts that you've done before. They could give you these to solve trig questions as well. And as I've stated, these can come in any shape or any form. So it's not just them giving you something to write as a product or as a sum. You could see this in a question and you'd have to convert it before you can actually solve the question. So it can come in any form. And of course, the textbook has quite a few examples of the different ways you can get these questions. So I'm going to do one where let me see. I'm looking for one where we just change from, we're using x or theta. I'm not seeing any right now, but I guess when we're doing the past paper revision, I'll be sure to include questions that have a variety of things being asked for. But for now, okay, there is one that has theta. Convert sine 9 theta plus sine 7 theta to a product. A product of terms. So we have sine 9 theta and we have sine 7 theta. So we must first look at which one is going to close. We must first look at which one we are referring to. So we have sine plus sine. Of course, it's the first one here, where it's 2 sine a plus b, and you know a plus b would be representing the angles here. So we're going to write that sine 9 theta plus sine 7 theta is equal to 2 sine 9 theta plus 7 theta divided by 2 cos 9 theta minus 7 theta divided by 2. So this is just 2 sine, that's 16 divided by 2, 8 theta cos theta. So is that clear? Any questions with that? Alright, so I take your silence as consent, so no questions on this one. Alright, so Danny is saying that they indeed got a formula sheet, and I'm assuming that these formulas will be on the formula sheet, including the compound angles, a few sign identities, and so on and so forth. I'm going to try and source the formula sheet if I can find it, and then I'll send it to you guys. Alright, so that would wrap up trigonometry, and that now brings us to two topics that we have to complete. We have functions. No, three topics. We have vectors, we have functions, and we have modulus inequalities. So what I'm going to do is I'm going to be sending you